Oh, does it seem really dark? No. Okay, it's not that dark. Good. Okay, so we are going to look at the derivative of the product of two functions. So if you've done the preamble, you already know. You know that it is the derivative of the first times the second plus the second times the derivative of the first. I get those backwards because it doesn't actually matter, like if you do first times the derivative of the second plus the second times the derivative of the first. It's just easier for me to say that. You will be required to possibly reproduce this fundamental definition of the derivative version of the product rule on a test. Okay, so we are going to go back to first principles and we're going to derive this product rule using the whole difference quotient. All right, so I want to take the derivative of f at x and g at x, and I want to use my, oops, that's h going to 0. I want to use my difference quotient. Okay, so that's easy. First of all, you get a ruler because some of the lines get really super long here. Well, that's embarrassing. Okay. So we start out innocently enough. So this is f at x plus h. Wow. F at x plus h times g at x plus h minus f at x times g at x. All right. And this is all over h. H is headed for 0, but it's not there yet. Okay. I can't do anything. I don't know how to handle this as the difference quotient, so we need to do a little bit of work with it. So limit as h goes to 0. The next part is just a little bit of magic with a pinch of pixie dust. Okay, this is f at x plus h, and that's kind of in the way. But if only I was subtracting f at x from this thing, it would almost look like the difference quotient. And here's a bit of magic, g at x plus h. You'll see what happens a little bit later. So I have willy-nilly added in this expression. To make sure I've got the same expression as before, what do I need to do? Sorry, I've subtracted it out. What do I need to do? I need to add it back in. Okay, good. So we have not changed this whole expression in any real way, except that it looks really a lot longer and really a lot more complicated, and it sort of is. And we put this whole thing over top of h. Okay, so this part right here is the non-intuitive product rule part that you're probably thinking, I would never think to do that. And yeah, you would be absolutely right. Okay, so limit as h goes to 0. What I'm going to do is I'm going to group these two, and I'm going to group these two, and I'm going to do a little bit of factoring, and you're going to see the difference quotient pop out a couple of times here. Okay, so I'm going to common factor out a g at x plus h out of this group right here. Ooh, and look what's left inside. F at x plus h minus f at x. Okay. Now in this, I am going to factor out an f at x. And look at what's left over. G at x plus h minus g at x. Okay. Big long line up here. This whole thing is still being divided by h. I haven't done anything magical. But as you can see, I have certain limit properties I can start to use. And you might notice that this derivative of the first times the second plus the second times the derivative of the first might be starting to emerge. Okay. This is this plus this over h. I can break that up into the sum of two fractions, and I can do the limit of a sum. I don't know. I'm going to do this in 2 steps, even though this is maybe a little bit onerous. Okay. F at x plus h minus f at x. And this is all over h. And this is plus. And this is the limit, h going to 0, of f at x times g at x plus h minus g at x. And this is also all over h. So you can now see that I have basically the difference quotient here, just sort of ignoring this part. And I've got the difference quotient for g at x here, just sort of ignoring this part. Now I also have a limit property that I can, the limit of a product is the product of the limits. So I'm going to do that next. Okay, limit as h goes to 0 of g at x plus h times the limit as h goes to 0 of f at x plus h minus f at x. And this is all over h. Okay, so once again, this is a fraction. This is g at x. I can look at this as being g at x plus h times this is a fraction. So I don't have to put my over h part on that. And I'm going to pull the f at x out in front of the fraction. And so this is limit as h goes to 0 of f at x times the limit as h goes to 0 of g at x plus h. I do not need a square bracket there. Minus g at x and all over h. Okay. The internet is smiling. All right. So we've gone through a couple steps. We've used some limit properties, but we've managed to get this down to this expression that involves two of the difference quotients with the limit as h goes to 0. Okay. A couple of tricky parts, subtracting and adding in. And then this may be what looks like a bit of voodoo here, where I just pull this expression outside. Believe it or not, I am all ready to go to press with this and apply my limit. So here we go. The limit as h goes to 0 of g at x plus h. Well, I can just plop a 0 in for h. And so this just becomes g at x. And then this is actually the derivative of f at x. So I'm going to use the prime notation. So second times the derivative of the first. Okay. Now I'm going to apply the limit as h goes to 0 to this. But there is no h, so I don't care. It's just f at x. So that's the first. And I'm going to apply the h going to 0 to this part, which is just the difference quotient. And that becomes g primed at x. So that is the first principles derivative for the product of two functions. Okay? So there's a little bit of voodoo there. The lines are super long, but that's it. Okay? So we can actually pull that out nicely with algebra. Okay, we're going to look at one example using the product rule. By the way, I might get these backwards sometimes. It's because there is a song, so I'll sing it right now, just so everybody knows it. I'm just going to make sure there's sound. When you're singing, you don't want to not get recorded, right? Second times the derivative of the first plus the first times the derivative of the second. Okay, so it's pretty easy to remember. It even rhymes, sort of, a little bit. All right, so believe it or not, in this unit, we only deal with, we start out dealing just with polynomial functions. And a little bit later on, when we do the derivative of trig and exponential and log functions, this makes a lot more sense. But for now, we're just going to do the derivative of the product of polynomial functions. And I'll explain why it seems a little bit silly. Okay, so I want to take the derivative with respect to x of 4x squared. And here's my second function. 2x cubed minus 4x plus 9. Okay, didn't really matter. When you look at that, you say, I know how to fix that one. I'm just going to multiply it all out, and I'm just going to use everything I already know. But since this is about the product rule, we are actually going to do this using the product rule. Okay. All right. I'm going to take this as my first function. Okay, so f of x is equal to 4x squared. And I'm going to take this as my second function. So g at x is equal to 2x cubed minus 4x plus 9. Now I'm going to take the derivative of f at x so that I can just plop it up into that formula. So f primed at x is equal to 8x. Okay, and I'm going to take the derivative of this one. G primed at x is equal to 6x squared minus 4. Okay, so I have the derivative of the first, I have the second, I have the first, and I have the derivative of the second. So I can now just put it into that formula. So I sing the beautiful song in my head and put it out. Yeah, so there we go. So g at x, which is 2x cubed minus 4x plus 9, times f primed at x, which is right here. So that's times 8x. And then f at x, which is just 4x squared. So plus 4x squared times g primed at x, which is 6x squared minus 4. Okay. So this is maybe the silly part. We can just expand and simplify that. But as you can see, sometimes it's actually helpful to write out the function and its derivative so that we can put it into that formula. Okay. I think what I'll do, I'll just leave it to the viewer to expand and simplify this. Okay, so you'd use the distributive property and you'd come up with a big long polynomial, collect all the like terms, and Robert would be your uncle. Okay, but anyway, there's an example of the product rule. Pick out the two functions, take the derivatives of both, put them into the formula, and it'll all work out. Okay, let's do the derivative of 3 functions. And in this case, we're going to apply the product rule a few times. And interestingly enough, we can extend this strategy to doing this for 4 functions. All right. So I have a function, f of x, and that is equal to 3 other functions, p of x and q of x, and, let's call this one, I don't know, p, q, r at x. Okay, so they're all functions of x, and we're just going to assume that they're differentiable everywhere. Okay, but my goodness, look at this. This isn't the product of 2 functions. This is the product of 3 functions. What am I going to do? Well, here's what we'll do. We'll look at it this way. This is the first function, and this is the second function. Eventually, we can make a song out of this. Okay. Let's see. Derivative the first time. Okay. All right. So I've just rewritten this. Now I'm going to take the derivative, and I'm just using the prime notation here. All right. So, we called this the derivative of the first times the second. So this is just the second. Okay. And we aren't doing anything magical with it, so I won't write it grouped like that. Plus the first. Oh, that's an equal sign. That won't do. The first times the derivative of the second. All right. Ooh, my voice cracked. Oh, well. Going through puberty a second time, perhaps, I'm not sure. This one is as good as it gets. This one, I have to take the derivative of q at x times r at x. But wait. This is just the derivative of the product of two functions. I know a formula for that. And the song goes, derivative of the first times the second plus the second times the derivative of the first. So I'm just going to sing the song. This doesn't change. Plus p at x times, oh man, am I going to get the song? Oh, derivative of the first, so q primed at x times the second plus the second, r primed at x, plus the derivative of the second times the first. The song just failed me there. Okay. All right. So here we go. P primed at x times q at x times r at x times p at x, so that I have to use my distributive property here, times q primed at x times r at x. Oh, sorry, everybody. That should have been a plus sign. Sorry, Internet. But it's easy to fix. Plus p at x. And I see that I've got my order mixed up here. Not that it matters at all, okay? But I'm going to just write it like that just so that you can see sort of the pattern here. All right. So that is the derivative of the product of three functions. Look at the pattern. This is the derivative times those two. This times the derivative of the middle one, and then those two times the derivative of that one. That's it. Okay. Product rule. Pretty easy, sort of, except for that first principles derivative.